Welcome back to KCET previous year question and solution classes. Today I will discuss 2018 paper from CMP, that means condensed matter physics and solid state physics and material science part also. So the question is like this: a lattice playing parallel to the x-axis makes intercept of 1 and 1. These are the intercepts 1 and 1 along y and z axis. The Miller indices are, the Miller indices we have to find. So we know that in this crystal concepts, Miller indices is very important to find the lattice constants, to find the intercepts, okay, or interplanar distance d. So to calculate all this, this Miller indices makes a very important role. Here these intercepts are 1 and 1 for y and z axis. The diagram is like this. So we know that h is to k is to l is equal to a by intercept along x, intercept along x, b intercept along y is to c intercept along z. Okay, so intercept along y and intercept along x. So this plane is parallel to x-axis. Parallel to x-axis means the intercept here is infinity. A, okay, is to b intercept along y is given 1 and intercept along z is given 1. Okay, since a is to b is to c is equal to 1 for a simple cubic. Okay, so therefore which is equal to 1 by infinity, 1 by 1 and 1 by 1. So 1 by infinity is nothing but 0, 0 and 1 by 1 is 1 and 1 by 1 is 1. So therefore h k l is equal to 0 1 1. So 0 1 1 plane is the correct answer. Okay. This is the question. The diamond structure has a space filling factor, that is space filling factor, that is dash that of the closed package structure. Closed package structure means here HCP, hexagonal closed package structure. Okay. So option is approximately off and approximately 1 by third and almost double the ratio they are asking, and almost the same as that of closed packed. So atomic packing fraction of diamond divided by atomic packing fraction of closed packet. So that is, which is equal to, atomic packing fraction of a diamond is 0.36 and atomic packing fraction of closely packed hexagonal closed packet is 0.76, I think 0.76 or 74. If you take a ratio of this, we will get approximately 0.46, and this 0.46 is nothing but 1 by 2, is nothing but 1 by 2. So off. So therefore it is approximately off. Answer is approximately off and option A is correct answer. The binding energy of an ionic crystal, this is an ionic crystal, depends on attractive interaction between the ions of opposite charge and repulsive interaction between ions of equal charge and van der Waals interaction. Okay, so ionic crystal, generally ionic crystals depends on strongly on attractive interaction between ions of repulsive interaction between ions of equal charge and attractive interaction between ions of opposite charge. We know that if two opposite charges place very near to each other, they try to attract, and if two equal charges, equal polarity of a charges placed together, they try to repel, and unequal type of charges, positive or negative charges, unlike charges. Okay, so if you place unlike charges very close to each other, they try to attract very strongly, and so therefore mainly it depends on A and B, and marginally it depends on C, van der Waals interaction. So yes, van der Waals interaction means it's an interaction between the outermost electrons, between the two atoms of an outermost electrons. So that is marginally depends for these ionic crystals, but mainly depends on equal charges. We know that plus charge and plus charge repel each other, and plus q charge and minus q charge, they attract each other very strongly. So option A is correct. So this is the question. Match the following description with the corresponding values of energy. KBT at room temperature, photon energy in crystallography, and photon energy at the red end of the electromagnetic spectrum, and covalent bond in acetylene. So KBT at room temperature, KB is nothing but 1.38 something into 10 to the power of minus 23, and T is 300. If you take this 1.38 into 10 to the power of minus 23 and 300, so then answer we will get in terms of electron volt. So that's why we should be divided with 1.6 into 10 to the power of minus 19. So after solving this, we will get approximately equal to 26 into 10 to the power of minus 3 electron volt. So I2D, 1 belongs to D. Okay, next, second one, photon energy in a crystallography. So photon energy in a crystallography can be calculated as E is equal to hc by lambda. H is, you know, that 6.626 into 10 to the power of minus 34, and C 3 into 10 to the power of 8 divided by lambda. So lambda, if they are not given, if there does not mention any above any value, specific value for that lambda, you can take that as a 1 Armstrong 10 to the power of minus 10. And we should express this in terms of electron volt. So therefore 1.6 into 10 to the power of minus 19. If we solve this, we will get approximately 8 electron volt, and that 8 almost all more than 8. So 11 to 12 electron volt, that is very nearer to C. Okay. So 1 minute, I will tell you that. Option B. So this is 8 kilo electron volt. So that's why it is, we will get here 12 kilo electron volt, and 12 kilo electron volt is very nearer to 8 kilo electron volt. So for 2 tends to C. Okay. Next, and third one. So photon energy at the red region. So red means, we know that the wavelength of a red is 620 something nanometer to 720. Okay, so it will comes under visible region. So therefore 628 I will take 10 to the power of minus 9 meter. So therefore E is equal to hc by lambda, and h is 6.626 10 to the power of minus 34 into 3 into 10 to the power of 8 divided by lambda is 628 into 10 to the power of minus 9 into 1.6 into 10 to the power of minus 19. If we solve this, we will get approximately equal to 2 electron volt. So 32A. So 32A, and next one remaining is fourth one. So the fourth one belongs to B. So fourth one belongs to B. This is the answer, and the options they are given like this. So these are the options given: 1 to B, 2 to D, 3 to A, and 4 to C. See, in this all these 4 options, so option number D is correct. See, 1 to D, okay, and 2 to C, okay, and 3 to A, okay, and 4 to B. So option D is correct. So this is question number 87. Consider the free electron model of a divalent solid having a simple cubic lattice with the lattice constant A, and let M be the mass of the electron. The electron energy, these are the options given. The electron energy at the face centered of the first Brillouin zone is given by, so that is something, and the electron energy is h cross square pi square by 2 ma square at the center or the corner of the first Brillouin zone. Next, the volume of the Fermi sphere is equal to the volume of the first Brillouin zone, and the volume of a Fermi sphere is smaller than the volume of a first Brillouin zone. So what is this first Brillouin zone? So let us see. So the first Brillouin zone definition is the smallest volume entirely enclosed, the volume is entirely enclosed, okay, by planes that are perpendicular bisector of the reciprocal lattice drawn from the origin. From the origin, a perpendicular bisector which is, for these are plane which are reciprocal lattice. So actually here it is not possible to explain in detail about this Brillouin zone, and also it takes some time. Go to the refer books like Kittel and Wahab for this Brillouin zone concept in reciprocal lattice concepts. Okay. So and definitely there will be 1 or 2 questions from this reciprocal lattice for your KSET every year. So this first Brillouin zone is also comes under that unit, and the answer is the electron energy is h cross square pi square by 2 ma square at the center of the first one is not an answer, and first one is also not correct answer. The volume of a Fermi sphere is equal to the volume of a first Brillouin zone, and this is the correct answer, because for a simple cube the volume is V is equal to A cube, and for a reciprocal lattice the volume is 2 pi by A, and this is also the volume for Brillouin zone, and that is 2 pi by A whole cube volume, and the lattice constant is 2 pi by A for Brillouin zone. So the volume of a Fermi sphere, the volume of Fermi sphere also 2 pi by A cube. So that's why the volume of a Fermi sphere is equal to the volume of a Brillouin zone. Okay. So for detailed explanation of this Brillouin zone, go through that lattice, it's a reciprocal lattice concept, and a Fermi surface. Fermi surface is also comes after specific heat of a solid, metals, free electron theory, and something all that. Okay. So the type 2 superconductors are characterized by two critical magnetic fields, Hc1 and Hc2. These materials are used for making very high field electromagnets, and this material shows Meissner effect up to Hc1 and constant, magnetization between Hc1 and Hc2. That means the magnetization is occurs between Hc1 and Hc2 from the option 1, and Meissner effect up to Hc1, and the magnetization reduces to 0 between Hc1 and Hc2, and Meissner effect up to Hc2, higher critical temperature, higher critical field. Next, Meissner effect only between Hc1 and Hc2. That means Meissner effect occurs between Hc1 and Hc2. So what is this Meissner effect? Meissner effect means when a specimen is placed in an external magnetic field, okay, and apply a transition temperature for a superconductivity, a magnetic flux is ejected from this specimen. Okay, so that is called Meissner effect. Okay, so that means, for example, a specimen is placed in an external magnetic field and cooled to a transition temperature of superconductivity, or cooled to a transition temperature for superconductivity. From this specimen, a magnetic flux is ejected, and that is called Meissner effect. And the type 2 superconductor shows a Meissner effect only up to Hc1. It shows a Meissner effect only up to Hc1 and still increases. Then what happens? Its magnetization reduces to 0 after Hc1. So that's why the magnetization is 0 between Hc1 and Hc2 is the correct answer. And Meissner effect up to Hc2, no. Up to Hc2 there is no Meissner effect. Meissner effect only between Hc1 and Hc2, no, because Meissner effect is up to Hc1, and after Hc1 the Meissner effect, the magnetization goes 0. Meissner effect up to Hc1 and constant magnetization between Hc1 and Hc2, no, is not our answer. So option B is correct. So this is question number 89. Contact between a metal and semiconductor is always ohmic, depends on the band gap of a semiconductor alone, and depends on the relative work function of the metal and the semiconductor near ohmic. So option number C is correct. So the contact between the metal and semiconductor depends on their work function. Okay, because there will be imbalance in the energy band gap. Next, match the following material with their resistivity value or the room temperature. So option number B is correct. If you calculate, we will get for deionized water, we will get 1.80 to the power of 5 ohm meter, and for fused quartz we will get 7.5 into 10 to the power of 17 ohm meter, and copper we will get 2.0 into 10 to the power of minus 1 ohm meter, and sea water we will get, for sea water we will get 1.66. So 1.66. Okay. So option B is correct. So this is B and this is C. Okay. Okay, for third, that means copper we will get 1.68 into 10 to the power of minus 18, and for sea water we will get 2.0 into 10 to the power of minus 1 per meter. Okay, so